Hello and welcome back. In this video we're going to look at three more indeterminate forms: 1 to the infinity, 0 to the 0, and infinity to the 0. Now you may think, 1 to the infinity, how is that indeterminate? 1 to any power is still 1. But remember, again, these numbers are not exactly equal to 1, they're just getting close to 1. Just like the numbers going to the infinity are not exactly equal to infinity because it doesn't really have any meaning, infinity is not a number, they're just approaching infinity. So there is going to be a race case between the base values and the exponent values for each of these three cases. In fact, in example 4, where we're going to have a 1 to the infinity type of limit, you're going to find out that the limit does not evaluate to 1. So this would be a good example to show why 1 to the infinity is not necessarily going to be equal to 1. It could be anything. It could be 0, it could be infinity, it could be another finite number. Let's find out what it's going to be. The technique for all of these, by the way, is we're going to first take the logarithm of the function. That's how we can handle functions where we have a variable in the base and the exponent. It's how we dealt with derivatives of, for example, x to the x. We took the log of x to the x so that we could bring the exponential with the exponential that was an x in that example down to the front. And then we were able to take the derivative from there. Same kind of principle is going to apply here. The problem is the fact that there's a variable in the base and the exponent. So we're going to use the log first to bring that exponent down in front, and then we can start to do what we need to do from there. The first thing in example 4, which is the limit as x approaches 0 from the right of 1 plus x all raised to the 1 over x, is figure out what type of limit this is. I mean, who knows? Maybe I'm trying to trick you guys and it's just a limit where you can plug in x equals 0. But it's not going to be. So in this case, if we plug in x equals 0, the base is approaching 1, right? The base is never equal to 1 because we're approaching, x is approaching 0 from the right. So it's 1 plus x is never equal to 1, but it's getting close to 1 from the right side, in fact. Now, as x approaches 0 from the right, 1 over x is blowing up to positive infinity. So this is of type 1 to the infinity. So our first step is going to be, instead of finding the limit as x approaches 0 of this function, we're going to find the limit as x approaches 0 of the natural log of that function. Let's write that out. Let's find the limit as x approaches 0 from the right of, let me highlight this, the natural log of our function. Yep. So we'll take that down here. Limit as x approaches 0 from the right of the natural log of 1 plus x to the 1 over x. Well, the first step is, the whole reason for using the log is that we can use that log property that brings the exponent down in the front. That's that third log property. So we have 1 over x ln 1 plus x. Now we can look at this limit as if it were a brand new limit and think, okay, what type of limit is this? Well, here we have the product of 1 over x and ln 1 plus x. The 1 over x part, we already did the analysis for that. That's going to infinity. So this part is going to infinity. Then we have times ln of 1 plus x. Well, if we plug in x equals 0, we get 1 plus 0, which is 1, and the natural log of 1 is 0. So it looks like this new limit that we have after applying the natural log to the original function is infinity times 0. And just a moment ago, we were looking exactly at how to deal with infinity times 0 problems. So we said, take one of these factors, like either the 1 over x or the ln of 1 plus x, bring it to the bottom of a fraction so that we get something like infinity over infinity or 0 over 0. Now it looks like the 1 over x is going to be much easier to bring down to the bottom of the fraction. In fact, the x is already down there, so we can just bring this x underneath the ln 1 plus x And now we'll have it in a fractional form. So we have ln 1 plus x over x. Let's check out what kind of indeterminate form we have now. Well, we said ln 1 plus x is approaching 0. And then as x approaches 0 from the right, x approaches 0 from the right. I love that kind of analysis, right? As x approaches 0, x approaches 0. So then this is a L'Hopital kind of situation, right? We have 0 over 0. We're going to be able to use L'Hopital. Take the derivative of the top, so that's the derivative of ln of 1 plus x. That's going to be 1 over 1 plus x, technically times the derivative of 1 plus x, right, which is 1, over the derivative of x, which is 1. Remember, again, we're not using the quotient rule. If you did have to take the derivative, if the top of your big fraction was a little fraction, maybe you'd have to use the quotient rule. But we're not taking the overall derivative of the big fraction. We're just taking the derivative of the top and the bottom separately, which is nice. It's actually easier to do that because you have smaller functions in the top and the bottom than as a whole. So now at this point, we can rewrite this in a simplified form. So just rewrite it. You end up with 1 over 1 plus x. And then you can plug in x equals 0, and you get 1 over 1 plus 0, which is 1. Now, sometimes people will accidentally stop here, and I've seen this happen many times. But remember what we found. We just found the limit as x approaches 0 from the right of ln of 1 plus x to the 1 over x, which is not what we were asked to do. We were asked to find the limit as x approaches 0 of just 1 plus x to the 1 over x. So we're almost there, though. All we have to do is take one last step. That takes 5 pages to do now. Take one last step, which is to say the original limit that we were asked to find what we could do is rewrite that function without changing it. We're just going to change the form of it, but not the values that it might have. We're going to rewrite the function like this. We're going to write it as e to the natural log of 1 plus x to the 1 over x. If you take a step backwards, we haven't really changed it at all, right? The e and the ln, if you do e to the ln of something, the e and the ln are inverse functions. They're going to cancel each other out when you plug them into each other. And so you would just get back to 1 plus x to the 1 over x. But the whole reason we're writing it like this is because we know exactly where ln of 1 plus x to the 1 over x goes. It goes, by all our work above, to 1. So that stuff in green there, the ln 1 plus x to the 1 over x, that, whoops, forgot, not writing the limit anymore, that whole thing is 1. So our answer is e. The limit as x approaches 0 of 1 plus x to the 1 over x is e. Right, so that's pretty cool stuff, I think. Thank you for watching, and see you next time.